And welcome to Module 5, Lesson 1, Chance Experiments. Okay, and before we go on, let's just talk about what the name of our newest module is, and it's all about statistics and probability. And it starts off quite easily in the sense with this this first lesson. We should be able to breeze through this one. In fact, I'm not sure many of you even need this video presentation, but I am giving it nevertheless. And once again, welcome to Module 5. One more module to go after this, which is Module 6. Presently, I do believe we are on schedule for you guys and gals to finish up by year's end, if you are staying on pace. That doesn't mean we'll have all of this done before testing comes about, but that is not something we need to be fixated on. We just want to understand this material. And statistics and probability, wonderful thing to get a good handle on now, this time of your life, because it will creep its head up there again in the future. Okay, and there's some new terms. There are new terms as we move into this study. Here are some of those terms right here. It said new or recently introduced. I don't remember you guys having been exposed to any of these terms yet. Compound event. Okay, very simply, this word compound, many of us have heard before in many different contexts. But a compound event is an event consisting of more than one outcome. Okay, from the sample space, and again, you're going to hear that term coming up quite a bit. This idea of sample space of a chance experiment. Okay, and again, we'll look at chance experiment as well. And an experiment, and necessarily it's not. I mean, experiment could be as simple as picking marbles out of a bag. Okay, or flipping a coin. Okay, when we talk about chance experiment. All right, inference. Probably a term that most of you have been exposed to. We talk about it mostly in terms of language arts, and this idea that inference is the act of drawing conclusions about a population using data from a sample, and that's of course the math definition. But inference is the act of drawing a conclusion from evidence that you have. Okay. It's not anything that is explicitly stated. For example, again, let's go back to let's say picking different colored blocks out of a bag. If we're picking different colored blocks out of a bag, you pick once, you get a red one. Pick again, you get a red one. Okay, you're getting the idea. You're able to infer after several times picking. And again, picking a block, taking it out, throwing it back in, mixing them up, picking, throwing it back in. If you continually get a red block as you pick, you could, at a certain point, safely infer that the majority of those blocks in there are red. In fact, you might want to infer that maybe every single block in there is red if you are picking, let's say, 100 times and you continually get a red block out. So that's this whole idea of inference, drawing conclusions about a population. Okay, that's not necessarily a population of people, but just a population of items using data from a sample. Okay, again, very mathematical definition of the term inference. All right. Here's one. I'm not sure we're going to get to this one anytime soon, but long run relative frequency. Okay, if you put those words together, long run, okay, and that means over the long run, over several times. Relative frequency, relative, that word means related to the situation or in a certain context. And of course, I think we know the word frequency means, how many times or how often. Okay? So the definition of this one they give you is the proportion of time some outcome occurs in a very long sequence of observation is called a long-run relative frequency. And again, that's really quite interesting, but that's exactly what I was just talking about, picking those blocks out of the bag and getting red, as many times. So that over the long run, if I picked out that a red block, let's say 9 out of 10 times, okay, well, 9 out of 10 would be my long run relative frequency in that case. Okay, here's one, probability. All right, and that's what we're talking about in this module. And probability, okay, now in this sense, they're calling it as a number between 0 and 1 that represents the likelihood that an outcome will occur. Okay, and again, this word very important, likelihood. All right, it is not a guarantee. Well, there are a few cases where it is a guarantee, and where the probability is 0, there is no chance of having an event occur. And a probability of 1 is 100%. Also means 100%. It means it's 100% chance it'll happen all the time. Okay, but anywhere in between, and that's usually what we deal with. Okay, we mostly deal with probabilities between 0 and 1, between non-existent and always existent. Okay, this is what we deal with mostly. Okay, and again, probability. All right, so probability model. A probability model for a chance experiment specifies the set of possible outcomes of the experiment. Okay, and that in terms is called the sample space. Okay, and also the probability associated with each outcome. Okay, a probability model. For example, if you're flipping a coin, okay, you can get heads, it's a regular coin, or you can get tails. Okay, so a probability model would state that you can either get heads or tails. Okay, and the chance of getting heads is 1 out of 2. Okay, tails is 1 out of 2, or we could also state it as 50%. Okay, and 50%. All right, so our probability model would state flipping a coin gives us 2 possible outcomes. Okay, and the probability associated with each of those, in this case, is 50%. Or we talk about chance sometimes as a 50-50 chance. Okay, in that case, that would be a heads or tails thing. All right, so here's some sampling, random sample. Okay, this idea of random, I think many of us have heard this word random before. We use it, teenagers use it quite a bit, just overuse it, let's say. Okay, that was random, that kind of thing, or it came out of the blue, which, it is, in context, I guess, it would make sense. But anyway, a random sample is a sample selected in a way that gives every different possible sample of the same size an equal chance of being selected. Okay, equal chance of being selected, which means if I put names in a hat, put all 14 of your names into a hat and shake them up, and again on pieces of paper or whatever, shake them up, put my hand in there and pull one out, everybody has had that same chance. So if we had 14 people in the class, everyone would have had a 1 out of 14 chance of being selected. So that was random. Now, if I go ahead and I put all the girls' names in there twice, okay, but the boys' names just once, okay, it's no longer random, okay, because the girls now have a better chance, okay, because they have their name. They have, so now we have, how many do we have in there? We would have 21 pieces of paper, or 21 names, because there are 7 girls and 6 boys. 8 girls, 6 boys. Okay, so we have 21, and so now the girls would each have 2 out of 21 chance. The boys would have just a 1 out of 21 chance. Okay, because their name would only be in that bag one time, where girls would have a better chance. So in this case, it's not, we've unrandomized it, okay, we've made it different. But in a random sample, it gives every possible sample of the same size an equal chance of being selected. Okay? All right, so a simulation, excuse me, a simulation is the process of generating artificial data, okay, that are consistent with a given probability model or sampling from from a known population. Okay, so a simulation, if we want to know, we want to gather some information about the entire United States population. Okay, now that's very large. Okay, the whole United States population is 350 million people. Okay, so that's a lot of people. All right, 350 million people. And of course, we're not going to poll, or we're not going to actually be able to ask every one of them a question. So we take a sample of that population, and then, because if it's consistent with the given probability model, or we're sampling from a known population, if we have the right percentage of women, right percentage of men, African Americans, Hispanics, whites, Asians, all of that, if we can get that together, but maybe we're only talking to 2,000 people, okay, that would be more or less a simulation, okay, simulating the whole of the United States. And we'll talk more about that, I think. I'm not quite sure where that comes up again, but very interesting things to know. Okay, so yeah, maybe this lesson will take a little bit longer than I thought, but hopefully you learned something there. I love knowing all of these terms and getting to know them better, and I hope you do the same. Okay. All right. Oh, here's a couple more actually. Okay, I'm sorry. I should have done those before. Let me get this out of here. Okay, yeah, a tree diagram. We're going to use a tree diagram coming up pretty soon. Not in this lesson, but a tree diagram is very helpful, very useful. It's not necessarily a term. It's more or less a tool. Okay, so yeah, and here it is, a tree diagram. Okay, consists of a sequence of nodes and branches. Okay, nodes and branches. You can see some nodes. Okay, you can see some branches coming off of those nodes. All right. Nodes and branches. Tree diagrams are sometimes used as a way of representing the outcomes of a chance experiment that consists of a sequence of steps, such as rolling, two number cubes, viewed as first rolling one number cube and then rolling the second. Okay, and this is this goes back to a compound event. You can see this word "and." Okay, in this case, we're talking about this example they're using is a compound event, more than one outcome from sample space. Okay, so for example, if you have this coin, you flip it. One possibility is to get a head, one possibility is to get a tail. Now, off of those possibilities, you could get then another. From a tail, you could get flip it again, you get another tail, or you can get another head. If you had flipped a head first, you can get a head or a tail. So what this does is it just kind of counts up all these possibilities, okay? And then you just extend it out. You might want to know, what are the chances now of getting a head if I flipped this coin, 20 times, all right? So I could just continue. So I'm going to go from here to here. Again, I'd have a chance of getting a head or a tail. Off of this one, again, a head and tail. And you can see how this builds, okay? Builds and builds and builds. Okay, that's a tree diagram. All right. This last term down here, it says uniform probability model. Okay, a uniform probability model is a probability model in which all outcomes in a sample space of a chance experiment are equally likely. Okay, equally likely. Now, we're going to find out, hopefully, how that differs from a random sample, or maybe they are one and the same. So, okay, without further ado, we've spent about 15 minutes talking vocabulary. Let's get into some problems, which are going to be very simple. Okay, so yeah, here we go. Let's just start right away. Have you ever heard of a weatherman say that there is a 40% chance of rain? I'm sure we have. Okay, tomorrow, or a football referee tell a team there is a 50-50 chance of getting a heads on a coin toss. I don't think football referees actually say that to determine which team starts the game. Well, these are probability statements. Okay, in this lesson, you are going to investigate probability and how likely it is that some events will occur. Okay, and this first example is a spinner game. If we were in class, it'd be a lot more fun to play this with a partner. But if you are at home and somebody is nearby, it would be nice to play it and see it happen. Just very simple. You know, in your binder you have a you have that diagram that looks just like this here. This circle split into 3 different parts: blue, red, and green. Okay, just like this. And if you took a paper clip and just a small paper clip, actually, the smaller the better probably, and just unfolded it in that fashion. Okay, unfolded it, and then what you do is you go ahead and hold it here. Okay, so you're going to put with the point of a pencil, okay, to make a spinner. So what you're doing is you're making a spinner. Actually, this is all going to change. I drew my pencil here. Okay, my very rough pencil, and I changed my paper clip because I didn't like it. Okay, yeah. So you see what you do, you're just going to hold a pencil, you're going to hold this paper clip with a pencil, and then you're going to push the paper clip, and it's going to spin, and it's going to land in one of those regions there, either blue, red, or green. Okay, so that's your cheapy spinner. All right. So first of all, if you're going to play with someone else, and excuse me, jeez, coughing. I have to hear this coughing all the time. If you're going to play with someone else, decide who will go first, because that's an important part of this game. Who goes first? Okay. All right. Because yes, important step. Okay, because that person will pick a color. Okay, and what color do you think? What color would you pick if you were to pick a color with this spinner that's right here in front of us? Okay, yeah, sure, I would pick green as well. Okay, you can't pick the same color. So let's say your mom goes first. She picks green, then you pick blue. You have to pick blue or red. You can't pick green as well. Okay. And then each person takes a turn spinning the spinner and recording what color the spinner stops on. Okay. And the winner is the person whose color is the first to happen 10 times. So we have to give it some ending period. So 10 times. As soon as someone gets their color 10 times, the game is over. All right. Play the game and remember to record the color the spinner stops on for each spin. Okay, so we're just going to gather some data from all of this spinning. And again, if you want to do it, you could do it yourself too. You can also play on your own. Do your left hand versus your right hand. You know, one goes first, or just create a fictional character to play with, or maybe prop up some stuffed animal to play against, or call your dog over, or something like that. You know, just take his paw or her paw and spin the spinner. Anyway, yeah, make it as fun as you can actually make something of this nature. Okay, and then after you've done this and someone's won, you can fill out these pages. Okay, and you know, I don't have this spinner in front of. Well, I guess I could do it. Hold on a second. Let me go ahead and pause for a second. Okay, so I invited a friend to come and play with me the spinner game here, and here he is. Welcome, Curious George. He was our Science Olympiad mascot, and he's going to play. And I'm going to let him go first because he's the youngest. Okay, and as the youngest, he goes first. And of course, clever little George picked green, and I picked blue because blue is basically my favorite color. Though I love lots of different colors, but blue, I would have to say, is my favorite. So here's how we started. Just give you an idea. All right. So I just put. We just started tallying up as George spun and I spun. Now we got to this point. I thought it was real curious here. Ooh, curious George. You can see blue was being picked quite a bit early on. And again, the fact of the matter is, these are chances. Okay, so 1, 2, 3, 4, 5. At this point, we have 6 blue. Okay, we have 6 blue. And we have, let's see how many green do we have. Let's get a little green color here. We have 1, 2, 3, 4, 5, 6. And then we had 1, 2, 3, 4 red. Okay, so at this point, blue and green are tied. And of course, with our spinner, you can see the way it's made that green has actually a much larger. It actually has a 1 out of 2 chance because there's half of the circle is occupied by green. Okay, whereas blue and red are 1 out of 4. because they occupy 1/4 of that circle. So, I mean, the fact that blue is performing as well as green at this point is pretty outstanding. Not that it has anything to do with blue being powerful color. It is all about chance. So, let me just go ahead and show you what happened next. Now we continued, and you see what happened towards the end. Green just came on strong, and 1, 2, 3, 4 did its thing. Final score was green 10, blue 7, red 5. Okay, will that be the will those be the results next time George and I play? Probably not. Okay, probably not. It won't happen that way. Okay, but again, maybe you had the same. So, if we go ahead and answer these questions here, do you think it makes a difference who goes first to pick a color? Well, of course it does. Okay, in this case, it does. All right, because of the nature of our spinner. Which color would you pick? Which color would you pick to give you the best chance of winning the game? Hello. Of course, green is the color we would pick. That's why George did that, and he won. Okay. So number 4 here says, below are 3 different spinners. On which spinner is the green likely to win? Okay, and let's go ahead and take a look at that. Oh, I'm sorry, I didn't do all these here. Okay. Now, in this case, spinner A, would green be likely to win here? And again, this idea of likely. And again, we're going to talk about these this probability scale really soon. This idea of likely, we would have to say it's a 50-50 chance. We would say not necessarily likely for green there. Okay. How about this one here? Well, here we have actually 3 out of 4 chance, which is like 75%, and that would be definitely a likely green. And then here, of course, we have, and that's less than 1 out of 4. Okay, and that would be a no. Now, again, I'm doing that from the perspective of knowing what this term likely means. You may not have answered those questions. You may have actually said, for example, you may have claimed that in this case, over here, that green might have been likely to have been spun upon. Okay, likely to win there. Okay, because it does have a 1 out of 2 chance, which is not bad, but which is not actually necessarily good. But again, this term likely, we're going to encounter that term right now. Okay, so what is excuse me, what is probability? Well, probability is a measure of how likely an event will happen. It is an event will happen. Okay, a probability is indicated by a number between 0 and 1, which is what we had talked about earlier. Okay, some events are certain to happen. Okay, and those certain to happen events would have a probability of 1. Okay, while others are impossible. Okay, and in that case, when we were spinning our spinner in our game, what were the chances of spinning a purple? Well, that would be impossible because there was no purple available. Okay. In most cases, though, a probability of an event happening is somewhere between certain and impossible. All right, which is again what we had discussed early. For example, consider a box that contains only red cubes. If you were to select 1 cube from the bag, you are certain to pick a red one. We say that an event that is certain to happen has a probability of 1. If we were to reach into the same bag of cubes, it is impossible to select the yellow cube. An impossible event has a probability of 0. Again, just repeating what I've said a few times so far. Okay, so why a probability of 1? Well, if we do have 5 white marbles in a bag, what is the probability of choosing a white marble? Expressed as a fraction, okay? And from this answer, we get this whole idea of why we say probability of 1, because that fraction would look like this, 4 out of 4, okay? 4 out of 4, and what is 4 out of 4? Expressed in its simplest terms, of course, it is 1. Okay. Again, if there were 5 red marbles in a bag, the probability of picking a red marble would be 5 out of 5, which is 1. Okay, and that 1 can also be expressed as 100%. Okay, 100%. And that 1, they're going to start you off looking, expressing it as 1, and then move eventually into percents. All right. So here we go. We have some explanations now of different descriptions of events, and then examples of those events, and then explanations. Okay, I'm just going to read that top one with you, and then have you just look these over yourself. There's no reason for me to just read these to you. Okay, some events are impossible. These events have a probability of 0. All right, you have a bag with 2 green cubes, and you select one at random. Selecting a blue cube is an impossible event. Impossible event, okay? There is an explanation would be there is no way to select a blue cube if there are no blue cubes in the bag, okay? Seems pretty straightforward and seems pretty kind of duh, but good just to clear up, okay? Clear up. All right, so go ahead and just read through those. You can pause right now, read through those, and then come on back. Okay, so we're back here. Let's go ahead and look at something we call the probability scale. How official this is, I'm not exactly sure. I must say I've never come across this, but I guess for our purposes throughout this module, and the 20-some lessons that we will be partaking in, we will go ahead and refer to this probability scale. The probability scale has all of these, let's go to these benchmarks on it. We have impossible, which is 0. We have unlikely, okay, which is less than 50-50, okay, a less than 50-50 chance. And we have that 1 out of 2 chance, which is 50-50, and it's equally likely to occur or not occur, okay? And then we have likely, which is better than 50-50, which is why when we were given, remember we were given that spinner with half green and half red, and I decided to say no, that wasn't a likely, you weren't likely to spin green. That is the reason, because it's not better, it actually sits right here as that 1 out of 2 in the scale, equally likely to occur or not occur. Okay? That's why I chose that before. Okay, anyway, and then we have certain, which is a probability of 1. All right? So here we go. We have exercises 5 to 10. Decide where each event would be located on the scale above, and place the letter for each event on the appropriate place on the probability scale. And I'll just show you what I mean by that. Let's look at that first one. A says, you will see a live dinosaur on the way home from school today. Well, that is going to be impossible. So I went ahead and put my A right underneath that. And the reason it's impossible is that there are no live dinosaurs right now, despite what you may have been told. Okay. Anyway, go ahead and do B through G, and come on back after you're done. Okay, so I'm just going to move through these relatively quickly. B was a solid rock dropped in the water will sink. Okay, well that is, why did I put that there? Impossible. No, that is not impossible. So I put it on the wrong end there. And there. Unbelievable. I think it's still going off. That's certain. Okay. Yeah, now a solid rock, and again I'm talking about solid rock. I'm not talking about something some of you may have encountered in your life, a rock called pumice, which is a volcanic rock which can actually float. Okay. Outside of pumice, pretty much a solid rock. All solid rocks will indeed sink. Okay. All right, and now a round disc with one side red and the other side yellow will land in the yellow side up when flipped. Okay, 1 out of 2 goes there in the middle. The spinner with equal parts numbered 1 to 4, that is a 1 out of 4 chance. That D is going to go in unlikely. Okay. Your full name will be drawn when a full name is selected randomly from a bag containing the full names of all the students in your class. Now, if we have 13 students in our class, okay, that's going to be pretty unlikely that your name will be picked. Not impossible, of course, but unlikely, 1 out of 13. Now, if you were in a class of 2 people, you would be equally likely, if you were the only person in that class, which does happen sometimes in homeschool, it's certain your name will be picked out of the bag. Okay, F. A red cube will be drawn when a cube is selected from a bag that has 5 blue cubes and 5 red cubes. Okay, that is a 5 out of 10 chance, or 1 out of 2. So that's going to fit right there in the middle as well. Tomorrow the temperature outside will be negative 250 degrees. Whether that is Fahrenheit or Celsius, that is going to be impossible. Oh, actually, I put it under the ridiculous part of the scale there. Okay. All right. Number 6. Design a spinner so that a probability of spinning green is 1. I'm not even going to pause and let you do this because, of course, we know that is not going to be that. That is going to be that. Yes. Design a spinner that's probability of spinning a green is 1, and that's going to be just a green, all green spinner. Okay. So here are a couple other ones, though. Number 7, 8. If you would go ahead and do those, you're going to create 2 more spinners based on the criteria that they give you. Do that and then come on back. Okay, we're back here, and here's what I drew. After making a mess, as you can see. Okay, this number 7 has to design a spinner so that the probability of spinning a green is 0. Okay, if it's an all red spinner, you're not going to ever spin a green. Okay, just ignore those little bits of green in there. Design a spinner with 2 outcomes in which it is equally likely to land on red or green parts. There's our spinner there. Okay, none of this is at all difficult. All right. Now next we have an event that is impossible, has a probability of 0, and will never occur, no matter how many observations you make. This means that in a long sequence of observations, it will occur 0% of the time. An event that is certain has a probability of 1 and will always occur. This means that in a long sequence of observations, it will occur 100% of the time. Okay, so just having that in mind, let's do numbers 9 and 10. I'll have you pause and do those here. Number 9, what do you think it means for an event to have a probability of 1 over 2 or 1/2? And then number 10 asks you the same about the probability of 1 over 4 or 1/4. Okay, so just jot down what you think that means, and then come on back. All right. Oops, sorry. I went and wanted to do this here. Okay. Yeah, so what do you think it means for an event to have a probability of 1 over 2? Well, of course, that just simply means and again, they want you to begin it like this, okay? In a long sequence of observations. Okay? And again, this is the important part here, okay? So, in a long sequence of observations. Because in the short term, again, if you have a probability of 1 out of 2, the truth is I can, and that's like a flip of a coin, I could flip a coin 10 times in a row and get 10 heads. It does happen, okay? And it can happen and it will happen. But if I did that, and I'm talking about a long sequence of observations, now this long sequence of observation maybe hundreds of times or thousands of times, okay? But eventually, at some point along the way, that probability will turn out to be, or actually the actual flips of that coin will turn out to be even for heads and for tails, okay? But it takes a long time sometimes, all right? And again, with this 1 out of 2, in a long sequence of observations, this event would occur, or it would occur half of the time. Okay, half of the time. All right? And again, for the number 10, 1 out of 4, Same exact idea. In a long sequence of observations, this event down here would occur about 25% of the time. Okay, 25% of the time, or 1/4 of the time. Okay, again, just knowing very importantly that we are talking about a long sequence of observations. All right, more reliable than the short term. All right, so here we are at lesson summary. Again, just to go over very simply, probability is a measure of how likely it is that an event will happen, and again, how likely, really important, never a guarantee probability. A probability is a number between 0 and 1. That's the way we're looking at it right now. The probability scale is here as follows, and it goes from impossible to unlikely to equally likely to certain. Okay, so we should, I'm thinking, see this probability scale pop up again in the next few lessons. All right, so a word about homework this time. Okay, I have decided to not include the exit tickets, okay, in your packets in this module. All right, and the reason I've done that is that those exit tickets, what they are actually designed to do, and what I might actually do is, with those of you who are on pace, I will administer the exit tickets for the last lesson that you are on when we meet in class. But I do not have them in the packets because I'm just thinking the problem sets themselves are enough to do as is. Okay, so go ahead. Good luck with those problem sets, and if you desire an exit ticket, maybe you found them to be useful, let me know and I could get one your way. All right, good luck.